So today I'll talk about the work that my co-authors, Sam Giro, Rick Scavira, Steve Gomez, Adam Bates, Bill Sanders, Hamad Akravi, and I have been working on with finding vulnerabilities in software-defined networking. So this was a joint collaboration between the University of Illinois at Urbana-Champaign and MIT Lincoln Laboratory. So I probably don't need to mention it to this audience, but SDN is clearly making its way into all kinds of networks. So certainly we've seen interest in the past from telecoms and cloud providers, and its popularity only continues to grow. Simply put, it offers a flexible alternative to traditional networking architectures. Even though you see a lot of recognizable names above, this is just a fraction of who's using SDN. So what enables this flexibility? So it's the idea that SDN is, as its name implies, software-defined or programmable. It's programmable in the sense that the network's control plane is now a network operating system, and that anyone can extend that by writing their own network applications. So and as a result, much like the mobile OS ecosystem, network app stores have started to come alive. So for instance, HP Enterprise has their own app store. So this means that anyone can extend the functionality of the network, write their own app, and submit it to an app store. So I won't advocate here for downloading untested apps and running them in your production network. But the fact that many third-party developers can write these apps and that practitioners can run them in their network poses the question, do these apps work well together? So particularly if any of these security-related apps are going to have critical impacts over the whole network operation. And in undertaking a risk assessment, we also want to know how they can be exploited. So say if I'm a developer writing a firewall application and I don't account for what another third-party developer's app does, can the combination of our apps together break the network? So in our prior work on cross-app poisoning from ACM CCS 2018, and based on the first talk today, it's clear that apps can cause problems. But what's even scarier is triggering vulnerabilities in those apps from the data plane. So in practice, what might that look like? So at a high level, the data plane can influence the decision-making in the control plane among various apps. That then causes the data plane to be reconfigured. So this kind of architecture is in use today by all of the major SDN controllers out there. So within that control plane, we have apps that register for events in the event subsystem. And in this case, some apps will register for data plane events, such as when a new packet gets sent to the controller. Some of those apps may also dispatch more events as a result of this packet, for instance, by modifying the control plane objects such as host and topology information from information learned based on this packet. And finally, some apps will make API calls to change the flow rules of the network. And so within all of that complexity, malicious data plane input can cause unwanted data plane changes by reconfiguring the network. An attacker just needs to be able to exploit at least one of the paths from the data plane input to data plane output. And as I'll describe in a moment, the way that's done is by leveraging missing events in the process. So we stumbled upon one of these vulnerabilities while working on cross-app poisoning, actually. So I manually discovered a vulnerability in the ONOS SDN controller's data plane firewall application. So essentially, an attacker here could abuse missing events in the app. So it's particularly concerning, though, because it allowed hosts to have increased lateral movement capabilities in spite of network policy that should have prevented that. So just imagine all of the malware out there that uses lateral movement to affect its attack. And now think about how this defeats all of those prevention policies from the network side. So for this vulnerability, I also wrote an exploit and shared it with the ONOS developers so that we could patch it. So to give you a sense of what the threats are and the difficulty of a discovery like this, I'll walk through the exploit in low-level detail. So just a warning that it gets a bit technical. So let's dive in. So we can assume that there are at least two hosts in the data plane. That one host, in other words, host 1, is malicious and is trying to gain communication with the victim host, in other words, host 2, to move laterally as part of a malware campaign. So to do this, the access control app is activated and registers for any host events with the controller. And the network operator adds in access control policies to basically say, prevent communication between host 1 and host 2. Host 1 sends a syntactically correct but semantically invalid ICMP packet, so in other words, a ping packet, with host 1's MAC address into the data plane. ONOS sees that packet and registers its MAC address, but not IP address. So note here that it realized that it has an invalid IP address, but it just didn't assign it an IP address to begin with. So it then generates a host added event. And so the firewall or access control app sees that host added event and that host object information. But since the host doesn't have an IP address, the app doesn't insert any flow denial rules that would otherwise prevent data plane communication. So looking at the code very briefly here, basically the event handler is on the left. Anytime it sees a host event in the access control app, it says, I'll try to process that. And then on the right, you see the code for the processing. Basically, it looks at every IP address of that host and sees if it matches the policy that's already been instantiated. Well, since that doesn't have an IP address, the call to insert a flow denial rule never gets called. So host 1 then attempts to send regular traffic to its desired victim destination, host 2. Since no matching flows exist, ONOS handles the packet. ONOS registers host 1's new IP address, its actual IP address, as a host updated event. Now, the access control app doesn't handle those host updated events, so it doesn't do anything. So as we see in the code on the left, it doesn't handle host updated, so nothing else afterward gets called. The packet then gets sent to a second app, which instantiates the flow allow rule and allows host 1 to communicate with host 2. So when all is said and done, the attacker is able to achieve lateral movement with just a few carefully crafted packets, which bypassed the intended data plane access control policy. So if you think this is complicated, you're absolutely right. Identifying this vulnerability involved pairwise inspection of many apps that might be installed on the controller. It also required some expert knowledge about how ONOS APIs and ONOS event handling works. And it required understanding of where we should expect event types to be handled. So we can't expect developers to understand all of the possible ways that this could happen here. So clearly, we need a procedural way of doing this. But what are the challenges here that make it hard to find these vulnerabilities in the first place? So first, there's no ground truth about what events ought to be handled, which we need to know to determine what's, quote, correct behavior. Essentially, this means that we're looking for the screen.
Can you act out the...
I'll just keep talking. So essentially, this means we're looking for those logic bugs that are hard to detect automatically. So second, traditional program analysis has to account for the operational lifecycle of SDN and for the apps correctly. And finally, not all of the event handlers that we find in the SDN's components may be exploitable. Does anyone have any questions so far?
Can you explain how do you find this stuff by analysis or by some automated mechanism?
It was actually, for the first one, looking at a lot of code and understanding what the event subsystem, how it worked. So it wasn't immediately clear to us how all of these, basically information that starts from a data plane packet, actually manifests itself throughout the whole system. So obviously we can see the first hop of like, once it enters the system as a packet in, then what does it do? But having a more automated way of doing that wasn't available to us at that time. So once we realized that with some time to check to time of use issues with race conditions, we were able to then detect it was actual vulnerability. And then we said, well, we need a system that shows us all of this in a systematic way. And that's what we did with our system. Yep.
In terms of what you may be going to talk about, but one thing I was wondering, this notion of interference between these network apps. It's certainly the case that people have done a lot of work in garden variety operating systems design, for example, to try to prevent that kind of problem happening. Do you see some of the techniques that people have used for separation of application space and so on in that environment being somewhat applicable to what we might do in sort of the network operating system space?
No.
Okay, never mind. You'll get to
I can answer your question offline if time permitting. But, yeah. OK, awesome. So all of those challenges from before. So we designed a system then to help us there that we called EventScope. So EventScope allows us to analyze SDN controllers and apps to discover where these cross-plane event-based vulnerabilities exist. And to give a preview of this, we were able to find 14 new vulnerabilities in the ONOS controller using this approach, which we were quite excited about. So let's take a look at the details of the system. So as we discovered, ground truth is a bit tricky here, if not impossible to determine, because most apps that we looked at were written by third-party developers, and their documentation about their correct behavior was quite limited. So to account for this, we clustered apps based on how similar they were in using events. Our hypothesis is that apps with similar functionality should handle events in similar ways, so any deviations from that show the potential for most likely problematic candidates. So to model this, we know that there is a universe of events, which we call event kinds. And so each event kind relates to a particular control plane object class, such as hosts or links or topology objects, as shown on the right. So for each event kind, then we assume that it has different event types. So for instance, the host event kind here has 4 event types that essentially describe the possible state changes that could happen. And based on how similar these events are handled across apps, we then cluster those apps into different categories. And we actually used pattern recognition techniques from machine learning here to cluster apps according to a metric of similarity, or distance. So in particular, we used the SymRank metric to do that, as SymRank essentially here says that 2 apps are considered more similar if they relate to similar event types. So based on this, we were able to identify the most likely missing event types across apps that merited attention as potentially problematic. So now that we have an approach for estimating ground truth, let's look at the program code itself. So we knew that we needed to do some static analysis here, but we ran into several issues. So the operational lifecycle of SDN has multiple entry points in which execution can be triggered. So for instance, it can be triggered starting from an app or from a data plane packet. And so even though we still need to generate call graphs and control flow graphs for our analysis, like we would for any kind of static analysis techniques, they're not useful just as is. So our solution here is to create a graph-based abstraction that shows us the necessary information needed to identify these potential vulnerabilities. So we call this abstraction an event flow graph. So let's take a look at how they're constructed. So first, we let each event listener within the apps or the controller be an entry point into the system. So as shown here, there's 1 packet event listener and 3 host event listeners. We then look at how these events are dispatched and subsequently listened to. So for instance, if we know that the packet event listener subsequently dispatches a host event, we can link that packet listener to all of the host listeners, with each edge representing an event type that that listener uses. Some event listeners will make northbound and southbound API calls to core services in the controller and the data plane, so we add those into the event flow graph as well. And then finally, putting it all together, we identify which listeners or API calls receive data plane input or affect data plane output. So in essence, this shows the entry and exit points from the point of view of the data plane hosts. So basically, where they can influence decisions from the data plane and where they can actually execute changes to the data plane configuration. So now we found that not all of the event handlers that we have here may be exploitable. So this is reasonable, given where the execution may occur in the operational lifecycle. So to account for this, we use the event flow graph to find viable traces. So to do this, we simply identify where the missing event type is not handled and perform path connectivity queries from the data plane inputs through the relevant event listener and to data plane outputs. So for instance, as shown here, the access control app here is seen as vulnerable, so we need to find viable paths that start from the data plane input here and out to a data plane output here. And then that's considered a vulnerability in our case. So we ran EventScope over ONOS, and in our evaluation, we uncovered 14 additional missing event type handlers within apps that were problematic. We reported these to the ONOS developers and requested CVE identifiers for them as well. So incidentally, all of the vulnerabilities involved host events and their indirect derivation via host-generated packets, which implies that the controller ultimately assumes that these packets from hosts are trustworthy. So let's take a look at one of the new vulnerabilities that EventScope helped us discover. So we assume here that we have 3 apps, the firewall and forwarding apps that were mentioned before, as well as a host mobility app. So that host mobility app looks for any hosts that have moved moved location in the data plane and removes the old flow rules that corresponded to where it had previously been located. So let's say that the firewall app successfully does install a flow denial rule that prevents host A, let's say, from communicating with other hosts. So another host in the network forges A's MAC address, which causes ONOS to think that the host A has moved. So how does this event flow graph help us here? Well, we can look at the fact that the host moved event is handled by the mobility app, in other words, to remove flow rules, and is not handled by the firewall app that would have otherwise added a flow denial rule. So basically, the flow denial rules get removed and never get reapplied. Although we don't automatically generate exploits here, the graph does give us a picture into what we should be looking for when we want to see how everything works together. And finally, we can see that once the firewall has been defeated, we can let the malicious host communicate with other hosts through that forwarding app. So we found that the event flow graph to be useful here in demystifying some of the control plane's complexity and to find vulnerabilities that would have otherwise been difficult to find. So to recap today's talk, we considered the cross-plane event-based vulnerability problem in SDN. So from a systems design perspective, what takeaway should we get from this? So first, it's clear that host can have an outsized effect on the control plane's behavior if their data plane input is assumed to be trusted. So when we do a security analysis as well over the entire SDN control plane, we should also consider how all of these apps work together collaboratively or maybe not. And finally, designers must design defensively here. And in this case, this means that they should account for all of the event types, even if they don't think their app will be affected. And we also showed that this is a real problem in practice by discovering and validating 14 new vulnerabilities for ONOS. So I want to thank everyone for their time. I'd also like to note, as a reminder, that I'm currently on the job market. So if anyone's interested in this kind of work, please get in touch. And so I'm open to answering a few questions, time permitting, but I don't think there is. So thanks.